Welcome everybody to this week's installment of the California Dreams Technical Seminar Series. It's been a while since I've been able to do the introduction for these, so I'm glad to be able to do that today and glad to be able to introduce today's speaker. Today we have Nuria Gonzalez Prelchik, who is a fellow of the IEEE and a professor in ECE at UC San Diego. Her main research interests include signal processing and machine learning for wireless communications and sensing, with several foci, including MIMO communication and others. She is a distinguished lecturer in the IEEE Vehicular Technology Society and has won many awards, including Best Paper Awards from the IEEE Vehicular Technology Society in 2022, another one from the IEEE Signal Processing Society for the Donald G. Fink Overview Paper Award in 2020. She has held a number of leadership positions in academic centers and programs, and we are glad to have her at UC San Diego, which is one of our partner institutions in California Dreams. So with that, I will just also add that we're going to try to save questions for the end. If you have questions anytime, please feel free to enter them into the question and answer box in the Zoom session, or raise your hand at the end of the talk and we will take questions then. So with that, I will turn it over to you, Nuria. Thank you very much for joining us.
Thank you. Thank you for the introduction. Hello, everyone. Thank you for being here today. I'm going to talk about an area that is very new, that is really very interesting for me, distributed integrated sensing and communication. I will talk about different aspects. I will try to provide an overview of the different works that are being done in different research groups in the world. It's not a talk about my own work only. I will mention in a couple of cases some of the things we have done. But I want to provide like a tutorial style presentation where I provide the overview why this is an interesting technology, how it's different from the general idea of integrated sensing and communication that has been exploring in the last years, why this is so new, this perspective, what are the challenges, and the focus of the talk is about the techniques to design the transceiver. How do we perform the operations in the receiver to allow the reception of the communication signal and the sensing in a joint way with multiple transceivers. And then I will conclude the talk. I will start with the motivation for this technology. If we think of the idea of integrated sensing and communication that was explored in the last year and is being studied in the standards like Wi-Fi standards, 6G, cellular, the idea is to use the communication signal for sensing. This is a communication-centric perspective. There are other people that are working on a radar-centric perspective where they use radar signals to embed communication information, but I will focus on a communication-centric perspective. So in that case, the idea is to use the communication signal, either the uplink or the downlink, also for sense objects in the environment, or even to have more information about the location of the users. In the case of a single link ISAC, not distributed, we only have a single transmitter and a receiver pair performing both sensing and communication. It can be in different configurations. In monostatic sensing, as you see in the figure, we can use the downlink and transmission to create echoes in targets that are then received also at the base station and analyzed for sensing. It can also be exploiting the uplink transmission, not only the downlink. And it could be a bistatic configuration where one transmitter is creating the downlink signal, for example, is refracting in a target and is being received either at the user or a base station. And it's just that bistatic configuration, it doesn't require so complicated circuits as for monostatic. But in general, the main problem of all these ISAC deployments that only exploit a single transmitter receiver pair is that they do not consider the full sensing potential that the network has. We have a network of base stations and users, and those nodes can jointly observe the environment and provide a much better perspective when combining all the observations together. We can see the limitations of single node ISAC here. I tried to summarize the idea that when we use single link ISAC, we are limited by a single perspective, a single view of the environment and the objects in the environment, and also limited by the equipment in those nodes. When we have multiple nodes performing sensing, we can overcome limitations like the coverage, the limited coverage and blind spots that we have with a single pair. Also the limitation of the single perspective, and if we have multiple nodes, we can have better angular diversity. In addition, this hardware that we have of the nodes, at the pair of nodes that are used for sensing in a single link ISAC configuration, by the number of antennas, the amplifiers that we have, the resolution of the converters. This is everything, all the sensing and communication performance relies on just one pair of equipments. And maybe it's not enough in many sensing use cases to achieve the required resolution and accuracy. It's also more fragile to blockage. There is no robustness to account for mobility and the dynamics of the channels. And the resources are very tight. We just have that equipment at the transmitter, the equipment at the receiver with the corresponding number of antennas and radio frequency resources, and they have to be used for both things, for communication and sensing. While if we have a diversity of nodes helping to perform the sensing function too, then we can split the required resources among many different nodes. And this is interesting and help us to overcome the constraints that I'm discussing here. In communication center in DISAC, what we are going to exploit is multiple nodes. It can be multiple base stations, multiple users, multiple base stations and users. It can also be a different type of nodes. There is heterogeneity here. We can exploit UAVs. We can exploit users on the ground. We can also include satellite configurations. And as you can see here, we can have many different configurations. For example, you can see here, this base station can be transmitting something, and this vehicle, the yellow vehicle, is a target and is being received the echo on this other base station. This would be by static configuration. Here, we are having, for example, this vehicle that is moving and is creating a synthetic aperture to observe the reflection from this pedestrian, who is a target for the vehicles on the road. So all this combination of configuration, base station to base station, multi-static, base station to users, multi-static, in the uplink, in the downlink, sensing with different elements, is very interesting and provides this spatial diversity, provides multi-perspective sensing, and improves both communication and sensing performance. I wanted to talk a little bit about terminology. When we say distributed ISAC, we in general mean collaboration too. I know that distributed does not necessarily imply cooperative, but the ISAC is often understood as an ISAC framework where these spatially separated nodes that are distributed operate jointly, and they are cooperating to perform the communication and sensing tasks. There are different terminologies that we can find in different papers. This is very new. Most of the papers are from 2025, so there is not really an agreement on the terminology. So you can find papers that talk about network level ISAC, others directly say distributed ISAC, multi-view ISAC, multi-perspective ISAC, cooperative ISAC. So in general, all of them talk about configurations where multiple nodes are cooperating to perform the sensing function. I also wanted to emphasize that this is not just an academic working line. 6G is seriously considering integrated sensing and communication, and of course, the distributed configuration, because the distributed configuration is required to support many of the use cases. Some use cases really require high precision spatial temporal processing. I mark there in those tables some of the use cases that the ones you can see in green have been marked by 3GPP as use cases that would benefit from the distributed operation. So we can really think as DISAC as a technology that can support real applications in transportation, in robotics, in many, many different configurations. I will talk a little bit now about the configurations and architectures for distributed ISAC. The figure on the left shows multi-base station distributed multi-view configuration, where multiple base stations process their own observations. As you can see here, the echoes on the targets are being created at each base station. And well, the advantage of this configuration is that it doesn't require high processing overhead and overhead in the backhaul in terms of the data being sent to a common fusion center to process them jointly. But we are not gaining much with this type of configuration. The accuracy is limited. In the two other deployments on the right, we have cooperative frameworks. The one in the center corresponds to multi-base station cooperative active sensing. So here, the remark is that we are going to send special signals for sensing, and there is cooperation in the transmission of the sensing signal. This can be interesting, for example, for sensing targets that are in a different space than the users. Here we can have a better coverage when we have several base stations coordinating the transmissions for sensing, and of course other base stations coordinating the reception. In the other case that we have at the right, we have a multi-base station cooperative but is passive. In this case, the communication signals are being used passively to collect the measurements of the multipath from these targets. There is not special signals for sensing in this case. Both configurations provide very large sensing coverage, and we are performing multi-static sensing, so we have a diversity of perspectives that give us robustness, improves the geometry of the problems that we will have to solve to locate the target's estimated velocity. But it has disadvantages because it requires the mutual calibration and the synchronization across the different base stations. I also wanted to comment on the difference between centric and non-centric architectures. In the figure on the left, you have a multi-use station cooperative passive sensing, and US passively sense the environment. This means we are exploiting the downlink communication signals directly for sensing. We do not send any special signal for sensing. And the joint processing of the features or decisions made at the different users is done in a fusion center. And this can be one of the users, like for example here using a side link, they can communicate results of the sensing functionality. In the one on the right, we have a centralized architecture. So we have the users, again, provide multiple views of the scene, in this case through multipath in the uplink. And this deployment is very interesting because it's compatible with the current cellular operation. In this situation, the coverage is limited, and there is a potential degradation due to occlusions because we are not really having this joint vision from multiple perspectives at the same time. Another difference I wanted to discuss is coherence versus incoherence in the processing chains that we develop. When we develop coherent processing, we exploit the synchronization in the phase domain. So the signals have to be phase aligned to exploit this kind of processing, and of course requires very tight synchronization in time, frequency, and phase. But it enables the true joint processing of all the raw signals at the same time, and of course provides the best gains in terms of sensing accuracy and resolution. And this is very interesting for velocity estimation and imaging, where resolution is really a key factor. But of course, it's very sensitive to synchronization errors and to errors in the positions of the nodes, because when we do coherent processing, we are treating the different nodes that are performing sensing functions as as elements of a distributed array. So the position of those sensing elements is part of the formulation of the mathematical problem. If there are errors there, we have also a distortion in the results of sensing. It also requires higher backhaul and processing overhead, because we have to share the data the raw data that different nodes are observing. With non-coherent processing, we can fuse directly magnitudes, energies, local estimates. We don't have to fuse raw signals. And it doesn't require this phase alignment. It's more robust, obviously, to synchronization errors, and works with decentralized processing, and scales very well. Because one problem of the coherent processing is that when we have many nodes, it's very, very, very difficult to achieve this time, frequency, and phase synchronization across nodes. But the drawback of non-coherent processing is that the accuracy is very limited for velocity and imaging. So the summary is that with the coherent processing, we can really do very, very well. But with non-coherent processing, we can scale the sensing solution to a larger number of nodes. I will talk now a little bit about the challenges of DISAC architectures. We have challenges at different dimensions. Here, I try to summarize the open problems that I see related to resource allocations and coordination. Here on this first portion of the figure, I want to talk about base station deployment and optimization. We need to now optimize the deployment of base stations for sensing coverage, for covering targets, not just communication users. And we have to put other things in the equation, like the geometric diversity. When I deploy the base stations, I also have to consider the diversity in directions that they provide to cover specific areas for targets. So this really introduces other metrics when we formulate the problems that we usually solve for base station deployment. Then we have the problem of dynamic node selection. In this kind of setting, distributed sensing, where many nodes, users, base stations can be part of the sensing process, we need to assign roles, and this is completely new. We need to assign to sensing nodes during the sensing functionality, they are going to be a transmitter, a receiver, or only a reflector. And this can change very quickly with time, because the environment, the propagation environment is dynamic. So this needs rapid reconfiguration. And of course, we have to talk about time, frequency, power, and spatial allocation. With these allocations of resources, time, frequency, and spatial resources, we can balance the communication and sensing performance. And maybe the better allocation for communication is giving us the really worst possible results for sensing. So it's really a very sensitive task doing this resource allocation. It's also important the role that this resource allocation can play on managing attacks or managing privacy preservation tasks. Like when we introduce spatial allocation, we can introduce some physical layer robustness to eavesdroppers, to jamming and other compromises. And finally, we also need to manage the configurations for sensing that we are going to use. Is it going to be all the time multistatic? Are we going to combine monostatic and multistatic, or monostatic and bistatic? And also we need to use this activation of configurations and modalities to account for nodes that may be compromised. So it's also related to security and privacy preservation. So it's really a myriad of problems that is really opening many interesting opportunities for research and development. On the transceiver design part, we also have to solve many problems. We, of course, usually have the precoding and combining task. We have to decide what precoders and combiners with spatial filters we are going to use at the transmitter and the receiver. And we have to consider sensing and communication metrics besides hardware constraints like power and number of antennas and other things. Of course, we need to estimate the multipath. The information about the targets is going to be embedded into the multipath components, into all the parameters of those components, direction of arrival, departure, delays. We need to perform time frequency and phase synchronization, or at least time frequency synchronization, if we don't want coherent processing. This requirement is completely different when we introduce the sensing functionality. We cannot use the methods that were used before just for communication. And then we have the sensing specific pipeline. So let's say we have estimated the multipath components, we have synchronized those values, so we have modified them to account for these timing offset, carrier frequency offsets, and now we have to process that corrected multipath information to obtain the information about the targets. And maybe there is part of the sensing functionality that is performed per node, but in other cases, we are going to have some functions like joint position estimation of the target across nodes. So we need to define all these algorithms and approaches to solve of these stages of the process. In the rest of the talk, I'm going to focus on the transceiver design, on all these different stages that you see here. The talk is not enough to cover all these aspects that I mentioned in this small section about research challenges. So I will just focus on the transceiver design from now on. I will start talking about time frequency and phase synchronization. How are we going to perform that? And I will start by describing the problem itself. What are these challenges related to time and frequency synchronization? When we introduce distributed sensing, we are trying to perform the observation of a target or multiple targets using hardware that is not synchronized. We have different clock sources in the transmitter and the receiver, where we have different local oscillators. So this causes synchronization errors in time and frequency. In particular, I will consider the timing offset, the carrier frequency offset, and the phase offset. The timing offset is the unknown shift in the time perceived by the receiver compared to the actual transmission time. There is this clock offset between transmitter and receiver in every system. For communications, this is not really important because everything is referred to the first multipath that arrives. So we don't really care about the absolute timing offset because it's not important for communication. But we will see that it is for sensing. And then we will have carrier frequency offset, mainly caused by the difference between the phases of the local oscillators of the different nodes that we are going to have here cooperating to perform sensing. And of course, we have phase offset caused by all these phase noises in the local oscillators, and it's not easy to control. So all these different clock sources or oscillators create all these offsets that need to be taken into account. I want you to see the impact of these offsets in the equation of the multipath channel. In this case, I'm considering a non-coherent transmission, which is common in cellular, and the MIMO channel is given in terms of a given subcarrier A and a given OFDM symbol K, and we have the channel metrics for that particular pair of subcarrier and OFDM symbol. In this equation, I'm assuming that all transmit antennas share a common local oscillator, and the same applies to receive antennas. If the different antennas have different oscillators, use different oscillators in their RF chains, then the equation becomes even more complex. In this case that I'm considering, I have a first factor here that may include some hardware impairments, including the phase noise, the phase offset caused by noise. This phase offset changes very quickly on a time scale of microseconds because it results from these rapid noise fluctuations in the electronics in the RF chains. Then you can see that we have the summation across the multipath. L is the total number of paths. We have the complex gain for every path. And what we have here in this first exponential is the delay. The delay has two components, has the true propagation delay and has the timing offset. So when our channel estimation algorithm estimates the parameters of the different paths, it's going to estimate this whole delay. It's going to include the timing offsets there. But for localizing the targets, we need to know the true exponential. In the other exponential, what we have is the Doppler frequency plus the carrier frequency offset that changes on a time scale of minutes to hours due to factors like temperature and component aging. So this is a slow bearing, but there is also the residual carrier frequency after compensation that can change much faster. So these parameters, delay and Doppler, are very important for sensing. But at the receiver side, the transmit signal that we are going to see is going to arrive time shifted by the propagation delay plus the clock offset, not just the propagation delay as we would like, frequency shifted by the Doppler plus the oscillator mismatch, not just by Doppler as we would like, and phase shifted by the clock derivative plus propagation. So really for sensing, we need to deal with these offsets to be able to perform the localization and imaging in the right way. You can see here a slide where I try to illustrate the impact of the timing offset in localization. How are we going to perform localization in general? We are going to exploit the delays corresponding to the different paths. We are going to group these different paths that we estimate to create clusters that correspond to static and dynamic scatterers. Of course, there are algorithms that can do that clustering and association of paths to targets. And then we are going to try to exploit those parameters for localization once we know that they correspond to the same target. I wrote here the equation that relates the expression of the propagation delay, tau L, with the position of the transmitter, which is known in this case, is with the position of the target, which is unknown, which is, for example, these people riding a bike. And we have here the position of the base station, which is known. This is known, is fixed. The network knows what the base station is. And then we have the position of the user, which is unknown in general. We will have to estimate it too. And again appears the position of the target. So basically I'm saying this propagation delay plus this propagation delay make the total propagation delay. That's what I'm seeing. This VC here is the speed of light. But channel estimation is not going to provide this true propagation delay. It's going to provide the propagation delay plus the timing offset. So if I use this directly here, I'm going to create an error directly in the estimation of the position of the user and the position of the target that I see here. In general, I'm going to process many equations like this to solve the problem of estimating the target. So it is clear that processing for sensing requires the separation of the timing offset and the propagation delay. But channel estimation, as it's used for communication, only provides this combined value. And let's see now the impact of the carrier frequency offset on bistatic sensing. Just to start with the simplest case, which is bistatic. In this case, you see the exponential here that contains the true Doppler and the carrier frequency offset. And these two terms also need to be separated for sensing, because we need the Doppler, just the true Doppler, to estimate the velocity, and we also need the true Doppler for imaging. So this residual, this carrier frequency offset that we see here, can really damage our estimation of the velocities, because may have a close value to the Doppler shift, to the true Doppler shifts. So it is really a problem. It can cause very large Doppler estimation errors. In communications, the way we deal with Doppler is basically mitigating, compensating for it. But that's not what we want to do here. We don't want to cancel the Doppler. We want to have it. We want to have, but separated from the residual carrier frequency offset. It's also important to realize that in some sensing cases, like for example, UAV detection and tracking, we may be interested on estimating the microdoppler. In those cases where we have the overall movement of the object plus some internal movements, like related to the rotors, for example, in the UAV, then we have an expression of the true Doppler that in fact depends on time. So we have a separation of the term that is fixed, doesn't change with time, which corresponds to the overall velocity, and then we have the microdoppler that is related to the micro movements. So in some cases, in some sensing situations, we're going to have to separate also these two different terms. And the communication techniques are not suitable for this. How does this stand to DISAC, to the distributed architecture? We saw that for the bistatic case, we need to estimate the timing offset and the carrier frequency offset to account for it during sensing. But if there is a clean direct path between the transmitter and the receiver, can always be exploited to obtain a stable reference. For example, if I have two base stations and one is transmitting and one is receiving to perform bistatic sensing, I know the true propagation delay because I know for the line of sight, I mean, because I know the positions of the base station. So from that propagation delay of the line of sight, I can extract the timing offset, because the timing offset is going to be the same for all the multipath components. But in general, in the multistatic case, I will have to deal with m transmitters and receivers and m multiplied by m possible synchronization mismatches. The offsets have to be defined with respect to a virtual time reference. So it's not possible to just use a reference between each transmitter-receiver pair. I need to find a common reference for all of them. And I'm not going to have a line of sight that is common to all of them, for example. So the problem is really much more complicated in the distributed case, because I need to align an entire network of links, and in time and frequency and phase if I want coherent processing. I'm providing here an example of a solution of a paper which is in arXiv. I think it's a very interesting paper. In this paper, authors consider multiple base stations transmitting and multiple base stations receiving. So these received base stations are acting as a distributed synthetic aperture. And they are using the line of sight echo for a given link to get a reference. And they first align, what they do is they align all the pairs to their own line of sights, because they are aligning the pairs to the own line of sights, and these line of sights are governed by the same physical clock. which is the speed of light and the geometry, this is an absolute reference. So if we are able to align every transmit-receive pair in a distributed setting to the true line of sight, then we are all aligning them together too. So it is really a very interesting trick. The problem is that this doesn't work when we don't have that line of sight. And in many of the cases, we are not going to have the line of sight. This trick can be also used for aligning the phase, the carrier phase, because when we have the timing, the true timing offset for the line of sight, we can also extract the phase of the line of sight carrier for the correct time instant and use it to align phases. In summary, the time frequency and synchronization, time frequency and phase synchronization is a hard problem. There are opportunities to provide solutions in non-line situations, non-line of sight situations. Also, when the nodes that are performing sensing are not static, are not base stations where we know the position and are fixed, it's not that easy to really synchronize during time. If we don't synchronize well in time, it's more difficult to synchronize in frequency. There are also opportunities related to synchronize when we have multi-band operation. For example, when we have carrier aggregation in cellular, what happens when we use different carriers to provide total bandwidth? How are we going to synchronize the different subbands? Also, some hardware may be lower cost and may introduce more problems. And of course, the robustness to positioning accuracy is really very important, that when we do this coherent processing, this time frequency synchronization, we need to know the position of the nodes if we want them to act as a distributed virtual array. I will talk a little bit about precoding and combining. In general, precoding and combining in integrated sensing and communication just with one pair of nodes is complicated. Consider, for example, this situation where we have a base station which is performing monostatic sensing, so the echoes of the downlink signal receive on the targets at the same time that of the transmission and at the same time as the uplink signals. It's a full duplex base station, and we need to design precoders and combiners to do several things, to deal with the self-interference, to have a good performance in the downlink. We need to design the combiners and precoders also to have a good performance in the uplink and a good sensing performance. I'm going to give you an example of the type of optimization problems that we have to solve. If I have this notation, I consider in a millimeter wave deployment with hybrid precoding and combining. So I have analog combiners at the base station, digital combiners at the base station, hybrid precoders also with an analog and digital part at the users. And well, following this notation, which is F in general for precoders, W for combiners, we are going to have an optimization problem where we want to maximize, for example, the spectral efficiency of the downlink users and the uplink users. And we consider the sum of all the users in the uplink, the sum of all the users in the downlink. And at the same time, to introduce the sensing performance, we are going to do it as a constraint. We want to provide a given signal to interference noise ratio in the direction of the targets. So that means for some directions, we are going to require some transmit and receive gain introduced by the precoders and combiners, right? For transmit gain, it helps to illuminate the target, and the receive beam helps to receive that echo from the target. And then we have other constraints. For example, this one, to cancel self-interference. We want that the analog combiner at the base station multiplied by the self-interference channel multiplied by the hybrid precoder is going to zero to help the full duplex circuit to pre-cancel the self-interference before analog to digital conversion, for example. That's why we are using here only the analog combiner. And then we have the unit modulus constraints of using an analog combiner implemented with phase shifters and the power constraints. So these kind of problems that in my group we have been trying to address are really complicated. So now let's move to a only communication scenario where we have multi-user communication, also multi-cell. Let's say we have distributed operation, but only for communication. So we are seeing the first slide, integrated sensing and communication, but we are not performing distributed operation. Here we are performing distributed operation, but only for communication. Let's look at the kind of problems that we have. In general, in this configuration that I'm showing here, that is called comp or multi-cell, multi-user MIMO, what we are doing is that one base station is sending data to both users, right? To this user and also to these other users through two different channels. And this transmission is introducing interference into this one. H12 introduces interference into H11. And the transmission from the base station 2 is also from base station 2 is also going to this user and introducing interference also in the other links. So the received signal, for example, at the first user is the direct signal intended for this user from base station 1. The direct signal intended for user 1 from base station 2, which is this one, plus the interference channels plus the noise, right? And we have to solve the design of these precoding matrices that have all these sub-matrices, F11, F12, F212, F22, and it's really complicated when we introduce, of course, more users and all the power and hardware constraints as well. So when we move to DISAC, the thing is that we have many objectives. We have, again, communication and sensing, and we have to optimize precoder and combiners are multiple nodes. There is multi-node coupling between the precoders and combiners. There is interaction between the sensing and the communication functionality. And this is further complicated by the hardware, by the self-interference, by managing all these different constraints and metrics optimizations at the same time, and the problems become really complicated. I'm going to discuss an example here for a solution that was just presented last year. And in this case, what we have is a number of base stations that cooperatively, as I explained before, cover new communication users. So they are using this multi-user, multi-cell MIMO configuration. And they are also trying to cover the area for targets. In this solution, it is considered that there is time frequency synchronization between base stations. This paper does not solve the synchronization problem, but requires that the base stations are synchronized. The sensing signal at the base stations include both monostatic observations and biostatic scatterings. So say here, this base station is receiving monostatic observations like this one, and may also be receiving transmissions from the other base stations for biostatic sensing. And we need to decide the precoders and combiners in all these base stations to maximize the performance for communication and sensing. In this case, how the authors do it is using the camera bound for target localization as the metric to optimize. They want to minimize this bound, the CRB bound for target localization. And the performance is introducing the constraint. For every user, the communication performance is considered the signal to interference noise ratio, and is established a threshold that we need to achieve for all the users. And then we have the per antenna constraints. So in this particular solution, metric for sensing is the metric to optimize. The metric for communication appears as a constraint to be fulfilled, and there are also other constraints. And these kind of problems are really difficult to solve, even in non-coherent situations. There are many open problems in precoding and combining. How to do monostatic sensing with a distributed configuration with all these self-interference and hybrid constraints. how to introduce the backhaul capacity limits. When we are doing this distributed sensing, we are using the backhaul to feedback sensing information, but there are limits on the data rate that we can use there. And we can introduce also those kind of considerations into the optimization problems that we need to solve to design precoder and combiners. And the metrics related to other sensing tasks like imaging may be more complicated, of course, than just the CRB for localization, because we have imaging, for example, there. We need to introduce other metrics. So there are really many precoding and combining problems to be investigated. And the last part of the talk, I will talk about the sensing processing chain. We need to use a different sequence of signal processing machine learning algorithms when we try to solve different sensing tasks, and they can be really very different. We can move from presence sensing, where we only want to know if there is an object or not, to other objects. In presence sensing, basically, what we want is a robust decision, and we want coverage. It's not about resolution and accuracy here. It's about having a robust decision about that presence or not. When we are talking about localization and target and tracking, we want to know where the target is and how is it moving, what is the trajectory. And here, multi-perspective is going to give us better accuracy. For target imaging, we want to know how the target looks like. We want to separate close targets. So we want to achieve super resolution here. So the sensing tasks you can imagine in all these different use cases for sensing are very different and require different algorithms. There are a number of basic tasks that have to be included in the sensing signal processing chain. For example, the multipath parameter estimation, the clutter removal, the Doppler range estimation per pair, and some of these tasks are clearly always going to be performed at every node. Some of the tasks like synchronization and beamforming, they can be performed jointly across nodes or maybe per node. And then there are other nodes that if we want to do distributed sensing, will have to be performed in a cross-node mode, like data fusion, obviously, and cross-node clustering on association of multipath components. So there is not really a universal solution. And what I'm going to do is to talk about one particular case for sensing. In this situation that I'm showing here, what we are doing is trying to use the beam training stage of a multi-user MIMO FDM signal to obtain the position of targets that are there. We are going to do single-shot target localization. It's like a first look at the environment and a first identification of the position of the target. We are not trying to do trajectory tracking here. And that's why this beam training stage is very interesting, because in the beam training stage, we are doing the beam sweeping. We are sweeping with beams in different directions a given area that we are trying to cover. And that is going to help us to discover targets in any possible position. The positions of the users are unknown in this configuration that I'm describing. So our problem needs to estimate the position of the users and the position of the targets that we have in the environment. That can be many. And we are going to have just one single base station and multiple users taking observations from different perspectives of the targets in the environment. I remind you again here about the relationship between the position of the target here, a given target here, and the position of the base station of the user that I was describing before. And this is the true propagation delay, right? So the channel estimation algorithm is going to give us this addition of the true propagation delay plus the timing offset. But the one that we want to use in this equation is the true propagation delay. And the challenges of using these kind of equations arise from the unknown UE positions and no association between the paths and the targets. I'm going to have a multipath here, but I don't know initially what are the correspondence between those paths and targets. And also I have the impact of the timing offsets, which are different for every user, right? The way we are solving this particular situation is like this. In this first branch, what I'm showing here, the operation is performed at every user. So at every user, we are going to do the channel estimation, the clutter removal, the synchronization, and the multibands path prodding. So basically what we are doing here is keeping at the exit of this, at the output of this block, we are keeping the first order reflections, which are interesting for localizing the target. Second order reflections do not fit into this equation. We cannot exploit them so easily for establishing geometric equations like this, right? You can see that this is just a first order reflection. This is the first part of the path, and this is the second part of the path. With second order reflections, it would be, and higher order would be much more complicated. So we just want to let's say, remove all the multipath components that are not related to the targets and are not useful for localization using this geometric approach. Okay, it's just moving by itself. So once we have that filter, let's say filter multipath, what we have to do is to cluster and associate paths corresponding to the same target and across multiple users. So we are going to put together all the filter multipath from all the users. So that information has to be shared. Either one of the users can do it or it can be fed back to the base station. And this joint clustering and association is going to give us, let's say, the target, the multipath associated to a given target. So I have groups of paths and I know what path corresponds to which target. And after that, I can establish a lot of delay equations and angle equations similar to the one I showed before, where I exploit the geometry of the environment. I know directions of departure and arrival, I know delays, and I have timing offsets. So I will also introduce the timing offset as a parameter to be estimated. In this solution, we are not synchronizing in time first. We are considering the timing offsets between the different pairs also as variables to be estimated. And they go into each of the delay equations that we are using to solve for the position of the user. And finally, we can exploit all this jointly, all this path information to obtain the values that we are looking for, position of the user, the targets, and the estimation of the timing offsets. I'm going to skip this other solution because the time is tight. Just to summarize some of the open problems on designing the transceiver are related to how to achieve robustness in scenarios that are dense or complex with multiple users, multiple targets, and how to define these different sensing processing stages for different applications like imaging, mapping, localization. Again, multiband appears here, how to process the measurements at different frequency bands. It's a similar problem to the one of processing measurements at different sites. And how to combine learning and conventional signal processes to solve the problem in the best possible way. And I will finalize with the final conclusions about the talk. I think we have seen that distributed ISAC extends integrated sensing and communication from single view to multi-view and helps to have a better robustness, better coverage, and a better accuracy. Coherence processing is very interesting. It's the type of processing that is going to give us the best possible sensing performance, but demands very tight synchronization in time, frequency, and phase, and requires overhead for all this joint processing of all the measurements. And we know that for many sensing tasks, this coherence is not really so important, but for others, like imaging, it is. When we design the signal processing chain, including learning aspects, we have to account for the specific architecture, the specific synchronization approach that we want to consider. All these stages are inseparable. And there are many open problems that we have to address related to resource allocation, deployment of base stations, coordination of all these resources, and the design of the transceiver. Thank you.
Thank you very much, Nuria. Do we have questions? While we're waiting to see if anybody else has a question, I'll start with one. Do you have any comments on the potential for heterogeneous integration in microelectronics to provide maybe more sensitive sensors while still getting more integration for digital processing on the signal processing and AI side to improve these kinds of systems?
I mean, I'm not a circuit expert, but of course I can see that that's a really interesting working line. Last year I was part of a proposal for an engineering research center where packaging sensors and the communication transceiver and all these aspects of integration at the circuit level, at the chip level, were one of the strong research components, research thrusts. And yeah, it's very interesting because when we are saying, I didn't have time to touch that aspect, but as things are evolving, there will be also standalone sensors that can be installed in base stations. For example, for UAV detection is very common, and tracking is very common, all these counter UAV solutions that exploit radar plus cameras, even audio in some cases. So multimodal sensing is very important. So the integration of standalone sensors together with the communication transceiver and how to share the data with very reduced latency is very important. But I think it's a very open area.
Mm-hmm. Thank you very much. Do we have any other questions? If not, we are right about at the top of the hour, so that was perfectly planned and timed. Thank you again very much, Nuria, and thank you, Peter, for sharing here. We have a QR code for the link to follow future seminars, and we have several seminars coming up at the end of January and beginning of February, and more to come after that. Next week, we'll have Eli Levinson-Falk from USC. The week after that, Sudhakar Pamarti from UCLA, and February 6th, David Harami from AIM Photonics. So we have 3 good ones coming up after Nuria's excellent seminar today. So thanks once again to all of our attendees and to Nuria for presenting.
Thank you for inviting me.
Bye, everybody.